After studying this module, you will be able to know about the production function of a multi-product firm. You would be able to derive the production possibility curve and derive the ISO revenue curve. All of these would lead to an understanding of the optimization of the equilibrium of a multi-product firm. So now let us consider the production possibility curve of the firm. Each product is assumed to be produced by two factors, labor and capital L and K. For each product, we have a production function such as X is equal to F1 within brackets L and K. This is the production function, the basic production function. And similarly, for Y, we would have another production function, Y is equal to F2 within brackets L and K. Therefore, the primary inputs, labor and capital, are common for the production of both commodities X and Y, but the nature of the production function may differ because the precise value of F1, which is the function for X, may differ from the value of F2, which is the function for production for Y. Now, let us consider therefore the Edgeworth box diagram. In the Edgeworth box diagram, what you can see is that unlike an ordinary map of isoquants of production, which as we have already seen are plotted in the xy space against the two axes, that is, on the y axis we are measuring capital, which is represented by K, and on the x axis we would be measuring labor, which is represented by L. Therefore, the total labor resources available measuring from the origin OX would be OX up to L. Similarly, the total capital resources available would be from OX on the vertical axis up to K, that is OXK. Now, this is when we look at the set of the isoquants which are given in blue. You would notice that there is a family of isoquants starting from the lowest isoquant A1 and it goes on to A2, A3, A4 and so on up to A7 and A8. Now, all of these isoquants are given in blue and they represent the isoquants which are for the commodity X. Therefore, for commodity X, the origin is OX. Now, because we have to optimize production and cost, as we are aware that input use represents cost. Therefore, we would simultaneously be optimizing the production as well as cost, that is minimizing the cost and maximizing the output for a given set of isoquants. Here, what you therefore see is unlike a single product firm where the set of isoquants would just stop with the available isoquants from A1 up to A8. Now, imagine that we are considering a multi-product firm. What is the difference and how are we going to incorporate both the products X and Y? Edgeworth box diagram is an innovation because in the two-dimensional space, the Edgeworth box diagram, unlike a ordinary quadrant, the first quadrant in which geometrically we depict the isoquants of production, in this Edgeworth box diagram, the innovation is that instead of being an open space like in the first quadrant in any map, this isoquant map, here what we have is two products. So, very cleverly what Edgeworth has done is to completely invert the origin. So, you have now two sets of axes. One axis is the y axis for capital, which is OXK, and the other axis which is inverted is OYK. So, OYL. So, therefore, now if we look at this, similarly if we look at the other axis, then it is OYK. Result is that instead of having a open space for the first quadrant, we have an enclosed space which is enclosed between two right angles. The origin of one right angle is OX and the origin of the second right angle is OY. Now, let us now consider what is the position within this box. We have already said that the blue isoquants represent the isoquant for the production of commodity X. On the other hand, we have another inverted axis which is representing the isoquants for the production of Y. Now, these isoquants are given in black and we have a family of isoquants which are coming virtually from top to bottom. So, the highest isoquant, if you look at it as such, is B1 and then it is going from the right to the left, so that we do not have a confusion about the isoquants. We shall be referring to the black isoquants for Y as from right to left and the blue isoquants for X from left to right. The properties of the isoquant remain the same, that is, for the product X, as we are going from left to right, the quantity of the output increases, and for commodity Y, as we are going from right to left, the quantity increases. Therefore, we have two sets of isoquants which are opposing each other. Now, all of this put together brings you to a picture, a figure which shows a crisscrossing of the isoquants pertaining to X and Y respectively. The question is this, that if we were to consider equilibrium, where would equilibrium take place? This is the first question. But there is a second question also, that is there any unique equilibrium? Because first of all, we would be considering the optimization with respect to one given pair of isoquants. let us consider the position at point Z. At point Z, what we can see is B4 and B and A3 are intersecting. Now we are considering two sets of isoquants. As I have said, the first one is in blue and is going from the left to the right, and the second one, this is for commodity X, and the second one is in black and is going from right to left and is for commodity Y. Now we are considering the possible point of equilibrium. Let us first consider the point Z. At Z, what you would notice is that Z is an intersection between B6 and A3. However, if we look at the intersection, you would notice that there are two perpendicular lines. What are these two perpendicular lines telling us? The intersection tells us that for commodity X, the consumption, the utilization of capital is OXK1, and the rest of the capital would be K1K. Now if you look at K1K and if we examine the isoquant B6, okay, then it shows that the marginal rate of substitution of isoquant B6 at this point would be different from the marginal rate of technical substitution for commodity X, that is at point Z, the slope of the two isoquants A3 and B6 are not equal. It is when the marginal rate of technical substitution between K and L are equal, only then can we say that there is an optimization. Now as opposed to Z, suppose we were to consider the point W. At point W, A4, which is an isoquant for commodity X, is just tangential to the isoquant for Y, which is B6. Therefore, the point Z which lies on B6 is not an optimal level of factor use. So if we shift from Z to W, what we notice is that B6 and A4 are tangential to each other. More of this would be clear if we consider the other levels as well. That is, if we are now, let us consider something like V. At V, what do we see? That at V, A3, which is the isoquant for X, is perfectly tangential to B7. So we have another point which is showing the tangency between the two isoquants. Similarly, we can draw a large number of points. Let us consider the dotted lines at point C. This again shows us that in between V and W there could be another set of isoquants, and if these isoquants are tangential at C, then C is also a point of optimization. What are we noticing? We said that we want to answer two questions. How does optimization take place? As we have shown, optimization takes place when the two isoquants are tangential to each other, and we have three examples for this at V, at C and at W. Similarly, we have got other pairings. We have a pair which is represented by A5 and B4. Similarly, B3 and A6, B2 and A7 and B1 and A8. As you go along towards the left from V, what you would notice is that again we have tangency between A2 and B9. So, some of the isoquants beyond B8 have actually not been named. Now, we have a set of points. Each of these points is given as a dark spot. Now, excluding the point Z because it is not an optimal point, we pick up all those points at which the two isoquants A and B as a family of isoquants, as a set of isoquants are successively in tangency with their paired isoquant. Therefore, as we have said, there are pairs. One pair, please notice, is A5 and B2 and B4. Similarly, you have A7 and B2. You have A4 and B6. So, these are all the pairings of isoquants. Now, if we were to join all these points, then you would see that there is a zigzag line. Please notice the red line which passes through all these points of tangency is a zigzag line. Now, if you look at the amount of capital that is utilized at any given point of optimal point, then one portion of the capital will be utilized for the production of Y and the rest would be utilized for the production of X. So, the total resources are given and they are optimally divided amongst the two. Similarly, if we at the same point, if we look at the utilization of labor, it would also show that some part of the resource labor is being utilized by X and the rest is being utilized by Y. Therefore, what we can see in this Edgeworth box diagram is for a multi-product firm, optimization of production takes place when the two isoquants which are opposing each other are tangential to each other, but there is no single optimal level of production and utilization of factors of production or inputs. There could be a whole range, there could be a path, and this path is known as the Edgeworth contract curve. We have just derived the Edgeworth contract curve. The Edgeworth contract curve tells us about various equilibrium points, that is multiple equilibria where the isoquants of production of commodity X and commodity Y are tangential to each other. Therefore, all these points represent optimal levels of production, and as we have seen, the total resources are optimally allocated between the production of X and Y. Neither is there any slack in the use of resources, nor is there any deficiency as far as the requirements of production for the given level of production in terms of inputs is considered. Now we will be considering how to derive the production possibility curve from the Edgeworth box diagram or the Edgeworth contract curve. we will be considering in this process certain given levels of optimum production. We are now considering the production possibility curve. You would notice that on the y-axis, OY represents the production of commodity Y, and on the x-axis we are measuring the production of commodity X. Both these, that is the production of Y as well as X, have been derived from a set of isoquants which were earlier considered in the Edgeworth box diagram. While examining the optimization process in the Edgeworth box diagram, we come across certain points of tangency between the isoquants which are named as A in the case of commodity X and B in the case of commodity Y. We are aware that there could be a number of isoquants like B1, B2, B3 and so on up to B8 or B9. Similarly, we could have a number of isoquants, that is A1, A2, A3, A4 and so on. Now, amongst these two sets of isoquants, there are only certain isoquants which are tangential to each other and represent optimization of production at certain given points. Let us imagine that V prime is one such point. At this point, what we notice is B7 was exactly tangential to A3. Therefore, we plot the point which represents the given quantity which is A3 of X, which combines with the given quantity of Y which is B7, and this combination is represented as V prime. Now, if the production of Y goes down from B7 to B6, then consequently, if there is full utilization of resources, it stands to reason that the production of X should increase. In this diagram, therefore, we notice that corresponding to B7, the production of X lies on isoquant A3, and corresponding to B6, which is a lower level of production of Y, the corresponding isoquant is A4. Therefore, it shows from the arrows that the production of Y goes down and the production of X goes up. However, because the resources are not uniformly productive when it comes to producing either X or Y, that is, we are considering the situation of increasing costs, what we find is that the relationship between the reduced production of Y on the y-axis from B7 to B6 does not lead to a linear increase in the production of X from A3 to A4. This is because of the convexity of the isoquants and because of increasing costs. Therefore, what we find is that the point at which Y is being produced to the tune of B6 and X is being produced to the tune of A4, at this point we plot W prime. We therefore have got two illustrative points, one is V prime and the other is W prime, and this represents the 2 points of tangency in the Edgeworth on the Edgeworth contract curve. But as we have said, as we move down in the case of production of Y from B7 to B6 and the production of X increases from A3 to A4. Now, if we were to join the points V prime and W prime, as we have just said, because of increasing cost or because of the convexity of the isoquants, what we find is that the relationship between V prime and W prime is nonlinear. It is going outwards, that is, it is concave to the origin. And if we extend this logic upwards from B7 on the y-axis, then it would become flatter and flatter as we approach the point of intersection P, which lies on the y-axis. And if we go from the point W prime towards the x-axis, which is P prime, okay, then the curve becomes steeper and steeper because of the presence of increasing cost. Now, if we were to join P, which is on the y-axis, V prime, W prime and P prime, which is on the x-axis, then we get a red line which is shown as a curve. It is downward sloping, but it is concave to the origin, and this is what we call the production possibility curve for a multi-product firm. Let us now consider the formal derivation of the production possibility curve. The slope of the isoquant A is given by minus of del K upon del L, which is equal to the marginal product of labor for X divided by the marginal product of capital for X, which is nothing but the marginal rate of technical substitution for X of L by K. So, the marginal rate of technical substitution is given for the two factors K and L in the production of commodity X. Similarly, the slope of isoquant B is minus of del K upon del L, which is equal to the marginal product of labor for Y divided by the marginal product of capital for Y, which is nothing but MRT as Y of K for L. The marginal rate of technical substitution for Y is the relevant slope of the isoquant of commodity Y, and similarly the marginal rate of technical substitution for X is the slope of the isoquant for production of commodity X. The point of tangency gives us the equation between the two isoquants on the contract curve, and the two slopes should be equal. Therefore, minus of del K upon del L should be equal to the marginal product of labor for X divided by the marginal product of capital for X, which should be equal to the marginal product of labor for Y divided by the marginal product of capital for Y. Therefore, the slope of the contract curve, say at V and W, could be represented by the slopes of the production possibility curve, which is PP from V prime up to W prime. Initially, these 2 points may be given as discrete points, but ultimately we would like to know the slope of the production possibility curve. Now, the slope of the production possibility curve, please notice, is not between two factors of production. It is not a trade-off between the utilization of labor and capital, but it is a rate of transformation between the production of commodities X and Y. Therefore, the slope of the production possibility frontier is minus of del y upon del x, which is equal to MRPT xy. MRPT xy is the marginal rate of product transformation, not substitution. A reduction in the level of y releases factors of production. Therefore, del Ly into MPLy plus del Ky into MP, that is marginal product of Ky. This shows how the total product is generated. An increase in the level of x requires additional factors of production. Therefore, del Lx is into marginal product of Lx plus del Kx into marginal product of Kx. Now, this is the amount of change in x and the additional factors of labor and capital required for the production of the increased level of x. Now, we have seen in the production possibility frontier that as we move from V prime to W prime, the production of x increases and the production of y goes down. If the factors are to be fully employed, then the quantities released from the decrease in y must be equal to the quantity used in the increase in x. Thus, minus del Ly should be equal to plus del Lx, and similarly minus del Ky should be equal to plus del Kx. This is a compensation of the utilization of factors of production released from the reduction in the production of y and an increase correspondingly in the production of x. This is a different kind of substitution. It is a substitution of both factors of production, some amount, some quantity of both factors of production from the production of commodity y, and then these released factors are being used in the production of x. So, therefore, if we have to put together this entire change which is taking place along the production possibility frontier from V prime to W prime, we would have to look at the total differentiation of the production possibility curve. So, the slope of the production possibility curve would now be del y upon del x. Okay, the change in y or the fall in y, we could call it minus because the slope is negative, minus del y upon del x shows that if y is falling in a certain proportion, then x would be rising in a similar way. So, this is equal to the total differentiation, which is del y into MP Ly plus del k into del ky into MP ky. This is the entire product due to which is falling in the case of y, and correspondingly look at the denominator, it is del Lx into MP Lx plus del Kx into MP of Kx. So, this whole expression tells us how with a change in y, with a fall in y, the two factors of production, labor and capital, released from the production of y are being substituted by their being absorbed in the production of x. Now, this whole process has to be done efficiently. For efficient production of the firm must stay on the production possibility frontier and not collapse within the production possibility frontier. This implies that the slope of isoquant A, which is MPLX by MPKX, should be equal to MPLY by MPKY, which is the slope of isoquant Y, that is isoquant B, which is for the production of Y. This is equation 2.2. Therefore, if we were to take the MPKX onto the right hand side, the equation would become MPLX is equal to MPKX into MPLY divided by MPKY, and this is equation number 2.3. Now, if we were to look at it similarly in terms of y, then we would have MPLY is equal to MPKY whole into MPLX divided by MPKX. So, these are interchangeable, equation number 2.3 and 2.4. Now, dividing the total differential by del Ly is equal to minus del Lx, we find that minus of del y upon del x, which is the slope of the production possibility frontier, is equal to MPLY plus MPKY whole into del ky by del Ly whole divided by minus MPLX minus MPKX into del kx upon del Lx. This is equation number 2.5. Substituting 2.2 into 2.3, the expression 2.4 and 2.2 and 2.3 into 2.4, we get a complex expression that is as follows: minus of del y upon del x, which is the slope of the production possibility frontier, would be equal to MPKY whole bracket MPLK upon MPKY kx plus del ky upon del Ly whole upon minus of MPKX whole bracket MPLY upon MPKY plus del kx upon del Lx. This entire first term in the brackets are equal to the expression 2.3, and the second term in the brackets are also equal by the same condition, that is del ky is equal to del kx. Consequently, the bracketed terms cancel out and the slope of the production possibility frontier is minus del y upon del x, which is nothing but the marginal product of ky divided by the marginal product of kx. Similarly, we may derive minus of del y upon del x is equal to the marginal product of labor, that is MPLY upon MPLX, that the slope therefore of the production possibility curve, which is the product transformation curve, can be simplified as minus of del y upon del x, which is equal to marginal product of labor of in production of y divided by marginal product of labor in production of x, which is exactly equal to the marginal product of capital in production y of y divided by the marginal product of the capital in production of x. Therefore, this shows that there is an optimal combination of both the factors in use and the output pair, which derives the highest revenue, maximizes the production, minimizes the cost, and gives you the optimal quantities of the two factors which can be used for finding out the overall equilibrium in the case of a multi-product firm. We shall now summarize what we have studied in this module. Each product is assumed to produce by two factors of production, labor and capital, and therefore we have correspondingly two factors of production. And then we have gone on to see how in the case of a multi-product firm we have an Edgeworth box diagram. In the Edgeworth box diagram we have a set of isoquants which represent production of X and a set of opposing isoquants which represent the production of commodity Y. Wherever these two isoquants are tangential to each other, we have optimal level of factor utilization. We have a contract curve, Edgeworth contract curve, which joins up all such efficient points of production. On the basis of this curve, we derive the production possibility frontier, which is concave to the origin, and it shows the possibility of production of two commodities X and Y in such a manner that when resources are released from the reduction in production of Y, then at the same time those resources are exactly utilized by the increase in production of X. In this manner, as long as the producer remains on the production possibility frontier PP prime, there is efficient production. There is both an efficiency in terms of the production of the two products X and Y, and also in terms of utilization of the total resources of the two inputs X and Y.